Okay, so we're now ready for a textbook introduction to spectroscopy. All right, so we're just going to go through these slides and give you what typically textbooks give you. So it's important to appreciate that spectroscopy involves the interaction of matter and light, right? So we're gonna shine light on samples and we're gonna get some information from it. Actually, what we're gonna do is we're gonna shine light on samples and we're gonna see what light gets absorbed and what light doesn't. Okay. So light, of course, as you've heard, can be thought of as either energy, or rather waves or particles. And the particles are called photons, and the waves are called waves. All right. And the wavelength of the waves of the photons is inversely proportional to the energy, right? So we know that energy is equal to hc over lambda, which is wavelength. C is the speed of light, and h is Planck's constant. So now frequency is directly proportional to the energy, and that is h nu. Some people write that as hf for frequency, right? Nu is the physics sort of term for, or physics symbol for frequency. All right, so you can see as frequency goes up, energy goes up, right? And as wavelength goes up, the denominator gets bigger and energy goes down, right? So wavelength is inversely proportional to energy and frequency is directly proportional to energy. Now let's review what the spectrum looks like, the EM spectrum. The light in electromagnetic radiation is a relatively narrow band of the increasing, and this is, by the way, this is you can see what's going on here, right? So here's increasing frequency is that way, okay, and increasing wavelength is this way, right, because they're inversely proportional. All right, so in this narrow band, 400 to 700 nanometers is light, right? So UV light has got a shorter wavelength, right? There's UV light, and UV light, X-rays is smaller yet, gamma rays is smaller yet, right? So that is in terms of decreasing wavelength, increasing frequency. All right, so we're interested right now in infrared. So we're going to be talking about that range right there. UV vis, of course, is also UV visible is a different kind of spectroscopy, which I'm not going to talk to you about, but that's in that range right there. So when we shine this kind of light, when we shine infrared, it's not really light, I guess, at this point, right? Because it's not visible. But when we shine infrared radiation on a sample, we measure what gets absorbed, and that is what we call infrared spectroscopy. All right, so different regions of the EM spectrum are used to probe different aspects, as I was just saying a second ago. Radio waves are used to probe NMR. I said in a previous conversation, this is interesting, another little textbook way to put it, the specific arrangements of all carbon and hydrogen atoms in the compound, I was calling connectivity in a previous conversation, right? And we do that with radio waves. You don't need to memorize this. It's just to helping you get a feel for where we're at, okay? That's for NMR. IR tells us functional groups present. Remember I told you we were going to call it that? And that is, and we'll describe IR in more detail in a few minutes. And UV spectroscopy talks about any conjugated pi systems yet. Conjugated means like two double bonds that are offset, sort of neighbors, not right next to each other, but off by one, okay? So this kind of a arrangement in a compound would absorb in the UV vis range. All right? So remember now, matter exhibits particle-like properties, and waves, let's see, and light exhibits particle-like properties too. Of course matter does, right? Mostly that's how we think of it. On the macroscopic scale, matter appears to exhibit continuous behavior rather than quantum behavior, but when we get down to small scale, like bonds, all of a sudden we can see that matter exhibits quantum behavior, and we're going to use that fact with spectroscopy to help elucidate molecules. Now, this is interesting too. A molecule is only going to rotate or vibrate at certain rates. That's not like so if you it's a little hard to appreciate exactly what could be meant by that. Matter of fact, I'm not even going to dwell on it. Let's say that it's quantized. They can only rotate and vibrate at certain rates and at certain energies, and those energies are the energies that get absorbed. I guess that's all I'm going to say about that. All right. And finally, for the electrons in covalent bonds, vibrational energies are separated by gaps. So remember me saying in a previous conversation that you can take a bond and sort of think of that like a spring, right? It's kind of like a spring, okay? And that spring can only stretch or vibrate in particular energy levels, and those energy levels are the energy levels that get absorbed. If a photon of light strikes the molecule with the exact amount of the energy needed to change this vibration from one step to another, then we're going to get an excitation, and with that excitation is absorption. Okay, IR light generally causes molecular vibration. Different types of bonds absorb different IR energies, and so when we see what energies get absorbed, we'll know what kinds of bonds are present. All right, and eventually the absorbed energy is released from the molecule through heat. All right, so put on your seatbelt, and we're gonna get deeper into spectroscopy now, the textbook way.